Afternoon, everybody. Are you guys able to see my screen?
We can.
All right. With that, I think I know people are starting to join. While they're doing that, we can go ahead and get started. Thank you for everybody for joining us. As we start out, we'll go ahead and just quickly introduce ourselves. My name is Kamal Baga. I'm one of the EVPs here at Revamp. I oversee the technical innovation team as I've been with Revamp for about 8.5 years, been in the industry for 15, and I work out of our Oakland office.
Hey, good afternoon, everybody. I'm Vivek Ramachandran, principal for the Power Systems Engineering Group. I'm based out of Austin, Texas. Been here at Revamp for a little over 5 years now, and been in the renewable space for about 12. To Evan.
Hey, everyone. My name's Evan Goldberg. I reside in the beautiful state of North Carolina in Raleigh. I've been with Revamp now for over 3 years as the principal in high voltage design and engineering. And I've been with the industry for going on 17 years. Kamal?
Cool. So today our team is going to walk you all through key considerations, technical challenges, and best practices for integrating BESS into renewable projects. A couple of housekeeping items to note. Depending on which version you have, you will either see a QA feature or a chat button that will allow you to submit questions while the presentation is going on. And at the end of the presentation, we'll also have some time to discuss those questions and then be able to allow people to come off mute to ask them directly if they'd like. Additionally, if you are looking for professional development credits for the webinar today, please send an email out to Chloe. Her email is going to be posted both in the QA chat and the chat windows. So if you're looking for those credits, please reach out to her directly and go from there. Right. Okay, before we dive into the content, I'm excited to take a moment to introduce or reintroduce you all to Revamp. Revamp is a utility scale renewable energy firm. Since we've been founded in 2016, we've designed over 26 gigawatts of utility scale solar projects all over the United States. Our development team has designed over nearly 300 gigawatts of renewable projects since 2016. We have a team of 148 rock stars that are committed to delivering resilient, high-performance systems that meet today's energy demands and lay the groundwork for a sustainable future. Our Revamp services cover a full spectrum of engineering and technical support for utility scale projects, from PV panel all the way to a transmission interconnection, from battery container to a transmission interconnection, and everything else that's between it. If you're looking for additional information, please check out our website and contact us at revamp-eng.com. As we're particularly talking about BESS today, we have years of experience working on BESS projects with a multitude of different manufacturers. This experience really allows us to anticipate and address unique technical demands of clients relating to BESS integration, and we have a holistic understanding of as to how the BESS is going to impact the PV system and how to design them together, hybrid, in all multitude of ways. And we're excited to talk to you about our capabilities today. Our team goal is to not only to support our clients with reliable designs, but to push the boundaries in renewable energy to create more adaptable and sustainable power infrastructure. One thing to note is these topics are a high level discussion points. We could literally spend a day on possibly just talking about one of these slides. So we will be going through a lot of different topics. Again, if you're interested in having deeper discussions with us, please reach out to us through our website. So site architecture. When it comes to BESS projects, there's two different types of architecture. There's AC coupled and DC coupled. Primarily, our focus today is going to be on AC coupled. AC coupled projects can be co-located with an renewable energy project. Typically, we call those hybrid projects, or they can be located independently. AC coupled BESS projects get their name because they are charged directly from an AC source. That could be the output of a PV system or directly from the utility. The one key factor about these projects is the inverters for AC coupled systems are bidirectional. So that allows them to work in 4 quadrants. So you can provide VARs, absorb VARs, provide megawatts, absorb megawatts. Next is the other type of BESS projects are called DC coupled. DC coupled projects are different because they're located directly within the array when we're talking about a PV system. So you have to have larger space around the inverters to have the battery containers. Typically, DC coupled systems have larger DC to AC ratios compared to PV only sites. DC coupled BESS projects are charged directly from a DC source like a PV plant. Usually there is a DC to DC converter that goes between the AC and DC inverter and the battery. This is due to allow for the MPPT of the inverter to maximize the power production of the PV. The good thing about DC coupled systems is they help recover the clipping losses that can be discharged later. So now I'm going to go ahead and turn it over to Evan.
Yeah. Good afternoon, everybody. So we'll now dive into the actual integration of BESS into some of your existing renewable sites and the thought processes that would go into that consideration. So Kamal, if you could start with the POI side. So as Kamal noted, there are 2 types of BESS with the AC and the DC coupled. And while some of the concepts that are relevant to AC coupled would potentially apply on the DC coupled side, we're going to primarily focus our conversation today on the main concepts as they apply to AC coupled systems, right? And so as we start diving into adding BESS to your existing projects, whether that's PV or wind, etc., you need to start with a couple of main considerations. For instance, are you going to be able to expand your POI limit, right? So when you sign those initial contracts or agreements and build your first project, perhaps you have a POI limit of 100 megawatts. Now, if you're looking to add BESS to the site, are you able to add that BESS capacity and production to that? So say 100 megawatts of BESS, 100 megawatts of PV, now you have 200 megawatts and you can dispatch that all at the same time? Or are you going to look to keep your POI limit? For instance, you have 100 megawatts of PV. If you have the 100 megawatts of BESS with 4-hour battery system, perhaps you just increase the duration of your production, right? So you expand what we like to call the shoulders of your production window to be into the evening hours or the high demand hours, etc. With those thought processes in mind, you'll be able to really start thinking about what equipment you have on your site already that are existing, what might need to be upgraded, what might be able to be replaced, etc. And you'll also be able to think about how that's going to tie into your existing projects, right? So you have the land available to you to place your battery system, whether that's an acre or whether that's 50 acres, whatever it may be. Are you planning to tie that into the existing substation and all the equipment you have there? Are you planning to get a new POI and share in other ways the equipment that you have? Those are types of things that you'll dive into. But primarily in the further slides that we'll get into, we're going to talk about having a shared substation. So, Kamal, if you might want to flip to the next slide. Yeah, so when we start talking about sharing a substation, you'll have your POI interconnect, you'll have your high voltage breakers, your main power transformers, and if it was a PV plant that you started with, you'll have all your collector and your feeders and your circuit breakers on a typically 34.5 kV side that bring all your PV feeders together and then step up to that POI. And you'll start having to think about the equipment that you have there already and what approaches you may take. So one of the more common designs that we see is utilizing a shared main power transformer between your existing feeders and your new to be added BESS, right? And so we have a general arrangement on the right. It probably wouldn't be laid out like this if when you first put your project together, you were only thinking about PV or wind, because you probably have your collector oriented in other ways. But the premise here is to kind of show some of what your options are, right? So you had all your PV circuit breakers, they were bifurcated, trifurcated, quadrificated, whatever you decide to do to each of your PV strings, etc. Now you're looking to add the BESS, right? So often one of the most common things you'll see is adding new circuit breakers to the design, right? So you'll expand your collector in whichever way your substation footprint allows for. And an example of that, if Kamal, you could click through, is going to be shown like here, right? So you'll have on one side, you'll have your PV feeders and the breakers. On the other side, you'll have your BESS circuit breakers, and you'll have your BESS feeder risers there as well. And, you know, one of the things that we often see with that is then you're able to add independent current transformers, right? Where depending on your region, the ISO, the utility, they may be looking to you to independently meter so they can see the charge and discharge of your BESS system as it relates to the rest of your plant's production, right? So having a configuration like this makes that very easy, where your circuit breakers are very much separated from your PV, and you know that'll probably end up helping you in other ways, such as how your feeders are routed. The other kind of concepts that we'll get into is perhaps when you had a PV plant only, you may have had capacitor banks, right? So Vivek, as he gets into his part of this presentation, will be able to give some more context as to when this decision gets made. When you add BESS to your project, it often is capable of handling a lot of the reactive power demands of your site, right? So it can provide VAR support for whatever your interconnect agreement aligns to, and perhaps, you know, if you only need a breaker or two for the BESS you're planning to add, you can end up repurposing those capacitor bank circuit breakers, and instead of tying a capacitor bank, you tie in your BESS. Other options could be, if you don't have the footprint available to go and add several more circuit breakers, perhaps if you're not increasing the POI limit, you can share your PV circuit breakers and the structures you have there already. But you know, with that, you kind of have to again think about, is that really a net gain for you, right? Because as I mentioned with those independent CTs, it's very likely that your project is still going to need to meter the production of your BESS separately from your PV. And then you're looking at designing riser structures to have independent CTs in a number of different ways. So as you start to get into the thought process of, hey, how can I bring in the BESS? Start thinking about how you want to bring it in, where it can go, and what's best situated. And that's the kind of thing that as we help you through your early stage design, we can point you in the right direction as to what might be the best solution for your project, right? Moving on from the actual connection of, say, your BESS and your feeders, there are other things to think about that kind of translate both to a shared main power transformer and beyond that you do need to think about as you bring BESS into an existing renewable project. And that is, depending on your BESS technology, a lot of times you need to provide auxiliary power to those devices, to those containers, whether it's for the battery management systems, for HVAC, etc. And that demand, in some cases, can be quite significant. If you're going with the Tesla Megapacks, for instance, that's not an issue because they handle a lot of that AC loading internally. But other technology providers, that is something that they're going to tell you that they have a load per their battery and per their system, and you're going to need to find some ways to address that, right? So a lot of times what you'll end up seeing is looking at adding a position on your collector to tap down from that 34.5 to 480 or 240, 208, depending on what battery you go with. And how are you going to do that? If the load is small, you only have a couple batteries, perhaps you can use a fused cutout. And if your fuse blows, it's not a huge loss. But perhaps if you're going with a much larger system, you need to add one circuit breaker. Maybe you need to add multiple circuit breakers off of different collectors and stuff. You may end up also needing to look into having a separate distribution circuit that comes in from your utility, which we would advise that you probably look in having an independent circuit. What we mean by that is not tied to the same transmission system that you're looking to produce your energy onto, because you don't want to have, say, a blackout on that circuit. Also disconnect your auxiliary power if you can avoid it. And perhaps if you can't avoid it, then you have to look into a generator or multiple generators, multiple switch gear as you configure and lay out your auxiliary system. So obviously all of this stuff takes up space. It requires bringing in additional circuitry from the utility, from generators, etc. And one of the big things that we often see gets forgotten is that you shouldn't be designing for what you think you need today. Rather, you should be designing for end-of-life augmentation when you add all that, what you need to add to your system, right? To make sure the end stage is provided for. All right. Kamala, if you want to proceed.
Yep. One thing that I'll just add real quickly, Evan, is it's also recommended that if you're aux power, if you can try to make it 480, if you have the option, that'll really be beneficial. So you can try to have a little bit smaller cable sizes compared to 208 for a 3-phase system. So we definitely recommend trying to get 408 as much as possible.
Absolutely. Voltage drop becomes a real issue at those lower voltages and the larger the site. So yeah, you're going to be dispersing it throughout. So great point. Yeah, so perhaps you're one of those lucky few that waited 2 years and you got your brand new spanking main power transformer and you want to put your BESS on a new power transformer, or you're operating in a region, for instance, ERCOT, where there's some value in perhaps having independent transformers. You're now going to have to think about some additional considerations, such as how are you going to connect this brand new transformer to your existing architecture, right? And a big part of that will be, you know, whether it was in an unplanned addition or a planned expansion to add BESS to your renewable site. And part of that premise is, Kamal, for instance, if you can go to the next slide, did you prepare to have the BESS added? So kind of like what you can see in our 3D model here, in the distance, you have two high voltage breakers and the disconnects that were feeding the the original PV plant, but being prepared for the future BESS expansion, you add a additional high voltage disconnect. Now it's just a matter of bringing that transformer in, putting it on a new foundation, bringing in the circuit breaker, tying all that in while you have that disconnect open. If it's an unplanned expansion, you're going to have to think about what it would mean to take an outage to tie in all that new high voltage equipment into your existing substation. Can you even fit it, right? If you plan for it, you probably set aside space in your yard. You built out your ground grid. You kind of know how you're going to drive into that yard. So one thing we would say that even if you don't think you want to add BESS to your project right now, think about what it might mean if you did, right? And you may find that the effort to make ready may be a valuable thing to do. And certainly, Kamal, if you could proceed. By planning ahead, you can also think about other considerations. For instance, what your MV bus ties might look like if you were to go with that approach, talking with your O&M team. So, for instance, if you could go on to the next slide, Kamal. Having a new transformer, you'll probably likely have a new collector bus. You can start thinking about tying those 34.5 collector buses together with a disconnect switch. And what that can mean is, if you're prepared for it, if you ever have to take one transformer out of service, you can close in that disconnect. And now, instead of losing the production of one transformer, you can now utilize the other transformer to push that power out to the POI still, right? So planning ahead, thinking through some of the ways that you may want to interface this new BESS into your existing substation can pay dividends in other ways. Next slide. Yeah. So kind of like we mentioned with the sharing main power transformer, there's also the same considerations for how are you going to get aux power to your BESS? How are you going to back up that auxiliary power? With a new collector, it's probably going to be a lot easier for you to plan ahead and add the circuit breaker, add diffuse disconnects, etc. But it's just something you very much have to keep in mind when you're doing your design in the early stages. All right. Next slide, Kamal. Sure. There we go. All right. So now you've thought about the primary equipment that you're going to have in your actual substation yard. What other considerations do you need to have? Well, if you plan for it, you're probably going to have space in your control enclosure for your additional equipment. What we mean by that is the new relay panels, your new energy management systems, perhaps. You plan for all the controls, all the additional SCADA, etc. And if you didn't plan for it, well, there's a very real possibility that your control enclosure is not large enough to handle all that, and you may need to add a new control enclosure now. And if that's the case, how are you going to tie the two control enclosures together? Because you will still have shared equipment, for instance, on the high voltage bus that needs to interface between the two, right? And don't just think about the relay panels, etc. You have to think about the bigger picture. Even if you have enough space for your panels, do you have enough space in your termination panels if you're using them to land all the cables from your new transformer, from your new circuit breakers, etc.? Does your cable tray have enough capacity to handle all the cables, your batteries, your panel boards? If you only design your panel boards for 10% spare, and now you're adding a whole third bay, like, do you really have enough space? Do you have to add the panel boards, etc.? And then I implore you, everybody's favorite item, right? Communications, fiber optics, right? Don't just wait till the last minute. This one always seems to get forgotten about, right? You're going to have potentially a lot more fiber optic communication with all of your batteries if that's the way that technology works, depending on your manufacturer. Or if you're using the megapacks, now you have 61850 perhaps that they want you to do for their arc flash management system. Do you have the means of bringing that all in? And please just start thinking about that one in advance, right? moving on, come. And talking about some of those O&M considerations, right? Like the power, et cetera. So depending on your technology provider for your batteries, will depend on if they have contractual requirements or manual requirements for O&M power, right? So perhaps you need to build an O&M office or warehouse for storing or housing the manufacturer's support staff, right? In that case, you need to look at power, right? Is it going to be 480 volt or 208 three-phase? If it is, it's likely not going to be already at your substation. So you'll need to consider if you have to bring in another circuit, or maybe if it is 240 volt that they need single phase, do you have enough capacity on your station service transformer? Don't forget that some manufacturers also require to have O&M power in the actual BESS itself, right? Receptacle, where are you going to get that power from? If it's from the substation, are you going to be able to run a circuit that long to the battery's voltage drop, or are you going to take it from your aux power, etc.? Then you have the actual facilities, right? Like, are you going to place the O&M in the footprint around the substation, or are you going to access it through the substation? Are you going to have it completely off-site? And if it's off-site, what are some of the servicing concerns that you might have, right? Like having to bring things on and off the site, and ultimately having communications back to the substation or to the battery energy system. If it all goes through the substation, do you have the connectivity? Do you have the conduits, the fiber optic capabilities, the internet capabilities, et cetera, to meet that? And then certainly, not the last requirement, but one of the other major considerations that you'll need to think about in adding BESS to an existing site is our favorite thing to think about, the AHA, the authority having jurisdictions requirements for that area. Do you need to bring fire and water support into the site? What does that mean if you have to do it inside your substation, bringing alarming into the substation, or bringing water near the substation? And what areas are those folks willing to access? What areas are they not willing to access, et cetera? So think about how you might lay all of that stuff out. All right. Come on, next slide. Come on, next slide. And now, given the major physical considerations, I'd like to turn it over to my esteemed colleague, Vivek, who will start getting into the far more technical study concepts.
Thanks, Evan, for some great insights there. For the power system impacts discussion as well, we largely focus on AC coupled PV and BESS systems. Now, from a reactive power standpoint, whether the BESS system can actually supplement the existing PV system in terms of providing reactive power, or if the two systems are to operate independently and meet their respective reactive power obligations, this would largely be defined within the interconnection requirements or interconnection agreements, or the preferences of the ISO or the RTO that's applicable to the project. These would also further define the overarching applicable reactive power requirements for the system, whether the older requirements which existed when the PVIA was created, for example, gets grandfathered in, or it's the FERC 827 requirements or the more expansive IEEE 2800 requirements. So let's assume we have a scenario where the BESS, in fact, can supplement the PV system in terms of reactive power production. This would provide a significant advantage to PV systems which are aging, and also to the PV systems that operate in the hotter climates. And Evan previously touched on repurposing certain the capacitor bank breaker. So this would be a scenario where that would be feasible. So the capacitor bank breaker, in essence, could be repurposed to bring in and connect the BESS feeders and enable an AC coupling between the BESS and the PV systems. Care needs to be exercised, however, if the capacitor bank was serving a dual purpose in the first place. right? And functioning as a harmonic filter, in which case, before deciding to make the swap, a closer analysis on the harmonic performance of the entire system needs to be taken into account. On the other hand, if the BESS is not approved to extend the PV system's reactive power capability, rather the PV and the BESS systems are to function independently from a reactive power standpoint, it still makes sense to study the two systems in conjunction just to understand the system's overall capabilities. It's often misleading, wherein the system capabilities are assumed to be the PV and the BESS systems independently, but the system capability does not always end up being the sum of its parts. So there needs to be careful assessment there on what the system can actually provide. Come on, next slide, please.
Yeah, real quick, Vivek, on that point, what we want to just make sure that everybody understands is the sum of parts, the PV systems losses and the BESS systems losses are independent of each other. You can't sum those up and say those are the total losses, because the losses are going through like the main transformer, main power transformer. If you're using a shared one, will actually be they're I squared, so they're actually exponential as they're squared, rather than they are linear.
Right. Yep. Good point, Kamal, as in that's something good to keep top of mind, especially given there are some round trip efficiency requirements tied into these battery systems. So the excess loss owing to the PV system current injection through some of the common elements does need to be accounted for. And that's a good segue to the next slides, talking about load flows. So in this case, we have a BESS system coming in that's connected to an existing PV system and sharing some facilities with the system, right? When the PV system is initially designed, if this expansion is not taken into account, a lot of the system sizing is done based on purely the PV system size. A typical example we come across is the main power transformer. These main power transformers get spec'd and designed for certain loading profiles. We all know the PV system generates during the day, and there's not much generation during the nighttime. So that's the purpose these transformers a lot of times are specifically designed for. Now, with the addition of the BESS, that loading profile will change, and that would impact the loadability criteria for the transformer itself. So that needs to get accounted for when we are running these load flow studies. Also, in most of these AC coupled scenarios where the BESS and the PV sit behind the same main power transformer, the net generation capability from the units, the BESS inverters plus the PV inverters, will almost always far exceed the transformer capabilities. So running different scenarios within the load flows and understanding what the dispatch constraints are, such that none of the systems get overloaded, is an important evaluation that needs to be undertaken at this point. And these set points for the different elements within the system needs to be then translated into the power plant controller, such that the actual dispatch lines up the studied cases and none of the elements get over. And I believe coming later on in the presentation, we'll walk over energy management systems and power plant controllers. Come on to the next slide, please. All right, yeah. So before we get into short circuit, a quick note here. So what we see increasingly with a lot of these PV BESS coupled systems is that the BESS yard is located really close to the substation. Yes, it helps with reducing the AC connection losses, but it also subjects the BESS system to higher phase and ground fault currents. Also, the addition of the BESS to a previously existing PV system means the BESS facility is now going to inject some additional fault currents into the PV system when there are those abnormal systems. Putting it in numbers, say the PV system, for the PV system, the fault current observed was 20 kiloamps prior to the BESS. Now, say with the addition of the BESS, it's kind of gone up 22 kiloamps or so. So there's an increment there that needs to get accounted for in these short circuit calculations. So Going into the neutral grounding reactor, the neutral grounding reactor essentially is a reactor that sits between the neutral of a Y winding for the transformer and the ground. And it helps limit the ground fault currents for the system. In all likelihood, when the NGR sizing was done, given we are talking about pre-existing PV systems, it was essentially the PV system limitations that were taken into account. And there is a possibility that the amount of limitation that the NGR is providing to the ground fault currents does not sufficiently protect the BESS system, right? So this may incur a change or an update to the size of the NGR. And in doing so, there is a requirement to revisit the coefficient of grounding as well as the arrestor sizing for the plant. Next slide, please. Now, let's assume the NGR is properly sized and the ground fault current constraints are kind of taken care of. Now, we are still left with the phase fault currents to deal with. And we can look at a couple of different scenarios. One scenario where, due to the proximity of the BESS to the substation, it's just the BESS system where the phase fault currents are exceeding tolerable limits. And a second scenario where, yes, the BESS is exceeding, but now given due to the BESS injection, the PV phase fault currents are also tipping over their tolerable limit times. So in these cases, we would need to introduce a current limiting reactor to help limit the amount of fault current that the system sees. But the current limiting reactor, again, is a reactor that sits in series with the rest of the system. And wherever it sits, it's going to see significant current flow during generation. So you will have some real power losses. You definitely will have reactive power losses, and there will be significant voltage drop. So prudently placing these current limiting reactors in a location where we can minimize its adverse effects would be advisable. So in cases where it's just the BESS feeders that's seeing a bulk of the fault current, right? It makes sense to have the current limiting reactor in series with the BESS breaker. So the effect of the CLR is localized, and it's just protecting the BESS system, and the drawback is also only observed by the BESS system. But in cases where both the BESS and PV feeders are kind of seeing this, you would require to put the CLR in series with the transformer, which means the losses will be seen on the entire system. Now, the current limiting reactor is again a big inductor. And for when the breaker operates for a fault and there's huge amount of currents going through the CLR, you will have a voltage spike on your system given the high LDI by dt. And that could result in transient recovery voltage issues. So this is something that needs to get studied whenever a CLR gets introduced into the system to make sure that the TRV capabilities of the breaker are in line with the TRV voltages it will be subjected to now with this new reactor. Come on, next slide, please. Okay, so on the thermal facet now, we had the PV system that existed with the MV home runs going into the substation. With the addition of the BESS, now we are introducing newer home runs that go into the substation. So there's going to be congestion in and around the substation. If during the design for the PV systems, there is an inkling, there is knowledge that there might be a future BESS system, some of this congestion can be managed by carefully placing the conduits coming out of the substation in select directions. You can see an example here to the right where the PV feeders are coming in from the north and the south of the substation, and the BESS feeders are coming in from the east. So both from a construction sequencing standpoint as well as a thermal standpoint, these circuits are largely decoupled. On the contrary, the other image, which is a SimCap output, kind of shows a system where the 4 PV feeders sit to the bottom and there's 2 BESS feeders on top. In this instance, they are a lot closer together. So yes, there will be thermal constraints, but even from a construction sequencing standpoint, given the PV feeders already energized and in operation, it would mean during the BESS construction, there's an outage on the PV system to enable BESS construction. An outage also means reduced generation during that period and probably a revenue hit on the project. So from a construction, maintenance, as well as definitely a thermal evaluation standpoint, better planning can give you a lot of benefits in how the MV fields come into the substation. Come next slide. So some other power system considerations that we won't be able to cover for this webinar, but that will be covered in the forthcoming webinars will be short circuit ratios when we are talking about these kind of coupled systems, temporary overvoltage, especially with different OEMs, or inverter manufacturers requiring different overvoltage limits to be honored, and then DC and AC arc flash. For the DC arc flash, we will possibly entertain some DC coupled notions, given how differently batteries versus how PV modules behave under short circuit conditions. And then, of course, AC coupled impacts on AC arc flash. With that, I believe I'll hand it back to Kamal to talk on energy management systems.
Hey, thanks, Vivek. So I was just going to give a quick overview about the energy management systems. And one of the critical features about the energy management system is when you're integrating a BESS project is you're integrating basically a secondary energy management system, which would be for the BESS. Most manufacturers that we know or equipment manufacturers for the BESS typically have their own energy management system for a variety of reasons. So the PPC can't directly talk to the batteries. It'll work through the BESS EMS in order to charge, discharge, get all of those commands from there. So this is a part of the system that should be, as you're building out the new BESS feature, they're discussing how that's going to be. Are you going to utilize the existing plant EMS and then build on top of that, or are you going to have to rebuild the architecture of it depending on how you are actually expecting the system to behave? Are they going to behave two independent systems? Are they going to behave together? So there's a lot of different ways of going through this. And how that's going to be, and updates to the plant SCADA of being able to get back information to your command center, operation center. But the main feature is being able to translate the grid operators' various conditions, whether they're asking for Q values, whether or if you're running an AVR control, etc. Having the power plant take those values from the grid operator and then translate those for the BESS and the PV commands. So this usually is one of the last activities that happens, but from Evan's point, it also has to do with the fiber infrastructure that has to take place, but it's also just a lot of commissioning into making sure that it all operates well together. We want to just thank everybody for joining us on our first webinar today. We have a couple of more of them that are going to be upcoming. And then with that, we're going to open it up to any questions.
Thanks, guys. We have a couple of questions in the chat. The first is, what is a typical end-of-life augmentation strategy? How much additional BESS capacity is typically needed over a project lifestyle?
I can take that if you guys want. It really is dependent on the manufacturer of the BESS. So usually most battery manufacturers will tell you what their degradation is going to be and what their expected degradation is going to happen. So they'll recommend the augmentation over the lifetime. Is it going to be augmented every 5, 10, 15 years, or and how that's going to take place? So we always recommend that you leave space for augmentation. The augmentation can be done in one of two ways. You can augment based on batteries, where you are taking older batteries from one container and moving them to another. So you can put brand new batteries in a new container. So there's like battery augmentation version of it, or you can do it where inverter augmentation, where you're just bringing in a whole new set of batteries. because technology is ever evolving, you have to make that decision of how do you want to produce with that. But our recommendation is always to leave space for augmentation, whether it's going to be augmented by batteries or inverters in the future.
Of course, with each of those different configurations, you'll have different other considerations, such as how you're going to connect that augmentation into the system, how you're going to supply the power and the load. And it's very incumbent upon the teams making that choice to understand what the manufacturer will do or suggest for their technologies. Kind of like Kamal was saying, if they're going to add it onto the end of the existing battery container, somewhat like the Megapacks do, that's going to be very different than actually pulling cells out and putting new cells in and replacing it in a different form, right? So just think through and talk through with each of your technology suppliers what way they're going to end up augmenting it.
Right.
Hopefully that answers that question. Go ahead, Vivek.
Right. A quick note there as well, especially when augmentation means adding inverters, you do want to kind of have a plan and process at the very beginning and work with your utility and ISOs, because that could impact your interconnection agreement and how the net power output from your plant is viewed from the utility perspective. So given BESS is relatively new with a lot of these utilities, there are differing approaches based on the ISO or the RTO you work with. So when you're adding inverters for augmentation, that's something to vary off.
Thank you. With DC coupled BESS, how often do you see a separate aux transformer used to power the BESS units versus a direct connection from the aux transformer to the PCU skid? Are certain PCU manufacturers better or worse for DC coupled BESS when it comes to this consideration?
So, Bill, thank you for your question. It is all site dependent, and it really depends on what that is going to be. So if you have a site that's in Arizona where it gets really hot during the day and you need to cool the batteries, I would recommend you may have to not utilize the PCU aux transformer for the BESS power, because you may end up losing that source and you need to keep the batteries cool. So it may be that you end up having a backup generator or a different source. So with DC coupled systems, it does become more complicated to run the aux power system. And how do you bring in that into to the system? There are definitely a variety of ways to do it, but one thing that's going to be really important is the location. So if you're, again, in Arizona, you're worried about heat. If you're in the northern states, you're going to be worried about snow. So is it going to be cool? So do you need to have heaters in there that are always working? And how do you plan for all of those? If it's in Florida, you may be able to get away from just doing that because their climate is a lot more stable, I would say, compared to other regions. And there's a lot of different infrastructure, and also how much risk do you want to take on as part of the as a manufacturer. So lots of different ways of looking at that. I think it's going to be very case by case specific.
One other thing to keep in mind with the DC coupled and stuff is that it's certainly going to be far more spread out than it would be if you had a singular battery yard, for instance, close to the substation. So you're not going to be able, typically in that case, to run 480 volts from a singular source out to each of these inverters, because the voltage drop would be just too significant for something like that. So you're going to be looking at a dispersed power profile, if you will, where perhaps you need to now run a medium voltage source out to closer to each of these areas if you can't use the aux transformer on the PCU to meet the demand, whether it's significant or not, from the battery manufacturer's requirements, right? So there's other considerations, and that can certainly add a cost to your project design.
Awesome. Is there a rule of thumb to size a BESS system for a PV plant, assuming no future expansion?
To be honest, I don't a rule of thumbs when it comes to these kind of things, it's all situational, and it really is going to come back to a financial analysis of what that's going to be, because different regions have different rates, and how you're actually charging the BESS is going to be also greatly impacted. The general uh, without a financial analysis, majority of what we actually see is that the BESS is typically sized to the POI limit of the PV. So if you have 100 megawatts of PV POI, you typically we see a BESS that's also matches it. Again, it all really comes down to is the financials analysis, which is something that we did not touch on in this because there's so many different regions and different utility requirements and other factors that have to be taken into consideration, the cost of energy at the time that you're dispatching, etc. So if you know that you might not going to do a future expansion, but you do want to have BESS, I would always recommend that you maximize it to the POI limit. It's because it's a lot easier to always with the utilities to downsize than it's to increase the size, because if you were going to increase it, you'd have to apply for a new LGIA. But if you were going to decrease it, it's quite easy to just do a MMA, which is like a material modification with Cal ISO and the other regulatory authorities.
Awesome. Any proportional relation between BESS size and the area required for that you would suggest for us to consider in regard to area required for BESS when we are considering BESS as a future option?
So the one thing that I would say that for BESS projects is we want to have an optimal you want to have an optimal design, and in order to do that, I would say you want to leave extra space, especially for aux power routing and MV routing of the collector. What we see a lot of times is that there isn't sufficient space for that, for all of those routing and other things, which makes it a lot more difficult. And in order to make that work, we have to put in thermal backfill, whether it's using concrete conduits. So there's a cost component to it. In general, it really comes back to is the technology manufacturer that you're utilizing and how what their power density is, because we've seen it in a variety of different ways, where how a 2-hour system and how much space 2-hour system would take compared to a 4-hour system. And now there are requirements of going up to an 8-hour or 12-hour systems, and all of those really change, because it really depends on how do you want to best dispatch it and what is the dispatching strategy. For example, if you had an 8-hour system, you can design 2 parallel 4-hour systems, or you can reduce it. So it really comes down to the technology and how do you want to go about that. It's probably not the answer that you're looking for. It's really also very situational.
Yeah, that Colin, great start to that. And you know, to add to it, right? If you have open land that you can get MV cabling into, you can get the aux power into, you can start small and just have a singular battery, right? And then as much open space as you have, kind of to Kamal's point, you can really, depending on the technology, et cetera, build it out. So if you ultimately meet the POI limit with the 2-hour battery, then you can start thinking about a 4-hour battery. And if you meet that 4-hour battery, then maybe you double it, right? Like you have all that space. You can really, provided the ISO or the utility is willing to take all this additional power, you can just increase the production timelines, right? Like the duration. It'll end up being a financial consideration in that point, though. But you have a lot of options for what you can do depending on how much open area that you do have, right? But a lot of times you're not going to have that much open area because you are paying for it, right? Like if you had that much open area, why, right? Like if you didn't put PV on it, if you didn't put wind or battery on it, like why did you have it in the first place? one other thing that I would note too that Kamal touched on a little bit when he started talking about the aux is beyond even just aux power. So think about what your AHJs may require, right? If they require setbacks for fire, if they require on-site water, how much space that'll take, and as your system gets bigger, what their requirements will do to change, right? So that'll be a conversation you have to have with your local ISOs, ASJs, etc. Right. So, great question.
What is your perspective on safety considerations when adding BESS for O&M activities? Do we have to look at other or new lockout, tagout, and isolation practices? As in substations, we now have chemicals on site. Are eye washing stations needed? What other safety considerations can you think of that we should consider when deciding to add BESS?
Yeah. I mean, at this stage, starting off, kind of leading off the response, AHJs are very much concerned about the safety of their BESS systems. You know, we've seen it vary across the country depending on where these projects are installed, about fire departments saying they're just going to sit back and watch them burn, to wanting to have options to essentially connect up to a dry pipe and push water from an offsite location in flood some of these batteries. And we're seeing more and more requirements come out from NFPA and other regulatory entities about how they want to make these systems safer, or make it so that the responders can feel safe responding to them, or provide at least some additional guidance in the early stages for these types of projects. So absolutely, in terms of like chemicals and all that stuff, you're going to see for sure more on the fire suppression side coming out. Which, there's a lot of talented firms that are working with the manufacturers on figuring out how to best suppress the thermal considerations for those. Talking about like lockout, tagout, and isolation practices, we say it a lot, but we see technology manufacturers take different approaches, and not necessarily to call out any specific manufacturer, but Tesla is a good one, right? As one of the big ones in the field today, we do see that they have O&M considerations that they require, right? And one of those things, for instance, is arc flash safety, right? They have a requirement that the arc flash be limited to a certain level, and if that can't be done, they want to see a system in place that measures the current and then communicates upstream with the substation using 61850, for instance, to be able to protect and isolate the units so that their techs can go into the batteries and not have to wear the heavy duty arc flash protection gear, right? And they have other requirements as to how you are going to lock out, tag out, and they have whole manuals, right? And we're seeing other manufacturers follow suit in terms of publishing how they want to handle the lockout, tag out, or the maintenance requirements for their systems. So again, very much technology dependent, but it is something that is becoming far more prevalent in the field now that things are getting refined, right?
Awesome. We are just about out of time. So if you submitted a question and we didn't have a chance to get to it, we'll make sure that one of these guys gets back to you with that information. With that, I'll turn it back over to Kamal.
All right. Well, thank you everybody for joining us. Please, once again, we have a couple of other webinars coming up. Please check out our LinkedIn page to register for those. And thank you again for registering. Again, if you'd like to get in touch with us for more detailed discussions, please check out our website. We have a communication form on that. Thank you, everybody.